Hello everyone. In this video we are going to talk about the kernel and image of a linear map. And no, I did not misspell kernel. This is how it's spelled in the mathematical context here. So let's start with the definitions. Our context will be that F is a linear map from vector space V to the vector space W. So the kernel is all the things that map to 0. So these are the vectors V and V such that f of V is equal to the 0 vector in W. And the image is just all the stuff that's hit in W. So what do I mean by that? Well, they're the vectors W and W such that W can be written as f of V for some V. Okay. And so we're going to see that these both have pretty close connections to one-to-one and onto. So we'll see that f is one-to-one if and only if the kernel of f is just the 0 vector, that's the only thing that goes to 0 from V, and f is onto, well, again, the image is everything that's hit, and onto means everything gets hit, so this means that the image of f should be the whole space W. Okay. So we'll talk more about those concepts later. The onto one follows basically from the definition, but one-to-one corresponding to a 0 kernel is going to require a proof. So let's just dig into some examples to really feel like we understand what these objects are. Okay, so let's look at some classic maps. So we're going to look at the identity map from a vector space to itself. So here, for the kernel of the identity, my claim is that this is actually just going to be the 0 vector. So I mean, that should make sense, right? Because this is definitely one-to-one. But let's see like why this actually works. So to check the kernel, a vector V lies in this kernel if and only if it is sent to 0. Okay, so if and only if the identity map on it is 0. But then we know what this means because we know what the identity map does. It sends V to itself. And so this is true if and only if V is 0. Well, that is it, right? We know that this is the only thing that's in the kernel. So that one's proven. And my claim is that the image here is all of V. Again, this is an isomorphism, so it should be one-to-one and onto, so it shouldn't be a surprise that I'm claiming that this is the whole space. How do we know it? Well, start with some V and V. How do we know it can be reached? Well, we know it is itself under the, if it maps to itself under the identity map. So then V is equal to the identity on V, and so it's in the image. V was arbitrary, and thus that means any vector in our space is going to be in the image, and thus the image is the whole space. So now let's look at the 0 map. So this will be a map from V to W where any vector V is always sent to the 0 vector in W. So in this case, again, V is in the kernel of F, if and only if f of V is equal to the 0 vector of W. But in this case, that is true for all V, right? Because f of V is always 0. And so this is true for all V in V. So here our kernel is equal to the whole space. What about the image? Well, what are the things in the image, right? We would need a W in W such that W is equal to f of some V. But here, f of V is always equal to the 0 vector in W. And so W must be equal to the 0 vector. This means that the image of f is just the single vector, the 0 vector in W. Okay, so now let's dig into some maps that are not just on general vector spaces, but are a bit more concrete here. So this one is the projection map onto the xy plane from R3 to R3, sorry. And in this case, again, you could see what's happening geometrically, right? We're just taking away the height, if you will, in XYZ space and projecting onto the xy plane. So the image should be the xy plane. That's all the stuff that gets hit. And the kernel should be the stuff that goes to the origin, which is anything along the z-axis. So let's see if that checks out doing the actual algebra. So we know that a general vector in R3, x, y, z, is in the kernel of this projection map if and only if P of it is the 0 vector, which in this case is just, right, 0, 0, 0. But we know what P of x, y, z is. It's x, y, 0. So when is this going to be equal to 0, 0, 0? Well, this is true if and only if x and y are both 0. And so basically, we don't care what the z-coordinate is, right? We just need to have the first two coordinates be 0. So we can conclude that the kernel of this map is the set of all things that look like 0, 0, z, where z is some real number. Okay. And that is exactly the z-axis, by the way, right, in three-dimensional space. So then what about image? So again, like some general guy, x, y, z, is in the image of P if and only if x, y, z is P of something, right? So I can't really use x, y, z again, so I'll say it's P of a, b, c. Well, we know what P of a, b, c is. This goes to a, b, 0. And so when is this going to be true? Well, it's going to be true if and only if x equals a, y equals b, and z equals 0. And so these first two conditions are really just saying x and y can be, whatever numbers. We know what they get hit by. They just have to match the first two coordinates. But the z equals 0 is an important condition there. And so the image is basically, again, the xy plane. It's going to be things that look like xy 0, where x and y are in R. Okay. So let's do one last example, and let's do something with polynomials. So we'll just do the differentiation map. It's one we're fairly familiar with. So in this case, we're going from P2 to P1, and now P of x is in the kernel of this differentiation map. Again, if and only if P prime is equal to 0. So when is that going to be true? Well, what does a general P of x look like in P2? It looks like ax squared plus bx plus c, right? So then we know its derivative is 2ax plus b. And so when is this going to be 0? This is going to be true if and only if a and b are both 0. Which, again, makes sense for us, I think, because, well, what things have derivative 0? It's the things that are only constants, right? And so basically we're left with just the c here. And so this is going to be true if and only if p of x is just some constant c. Right? And so this means that the kernel of my differentiation map is the set of all constant polynomials. Okay? So again, this map would not be 1-to-1, right? All constant things are going to 0. And so what about the image? Well, here we want to say start with a general thing in P1, right? So start with some ax plus b in P1. When is this in the image of the differentiation map? This would be true if and only if ax plus b is the derivative of some polynomial in P2. So it's p prime of x for something. And so we need to find the p, right? Does something go to it? So we just want to do the antiderivative, right? So this is true if and only if p of x is equal to a over 2x squared plus bx plus some constant c, right? These are exactly the things that have derivative ax plus b. And so can we always get ax plus b? Well, yes, right? Because a and b, we have the choice of making those, and then we can actually use any c. So in fact, we'll have infinitely many things that go to any ax plus b. And so the image in this case is all of P1. This is an onto map. Okay, so for your exercise, I want you to consider kind of the anti-differentiation map, which again we said in general is not linear, but is linear if we have no constant term here. Okay, so your P of x in P1 is going to its antiderivative with constant term 0. So I want you to find the kernel and the image of this map. All right, thank you for watching.